Okay, recording is rolling. Friday, October 1st. You guys just turned in your forces quiz and impact form. You guys turned that in before. And we're going to put together the graph and equation for the centripetal force lab. So what is the centripetal force applied by the weight of this hanging Play-Doh canister to hold the mass of this canister in a circle of some measurable radius of curvature going at some speed? Got four variables. What's that relationship? Right, so I'm going to switch my screen over. Let's say present screen 2, share that. All right, pull this up for you guys, period 5. Okay. Now, since there's 4 variables that we're juggling, you guys had to do 3 separate experiments. So who wants to share their data for the case of you were changing out the weight of the hanging canister? Who was changing out the weight of the hanging canister wants to share their data? All right, I will take a trip around the room and see if anybody has a page that looks like that. Okay. Just changing out the weight. Aha, I'm gonna borrow this. Thank you for. I have an anonymous contributor. It's gonna save us here. So the weights go, looks like 820 millinewtons, 23, 20 millinewtons, 25, 20, 27, 20, 26, 20, 24, 20, 43, 20. All right, so those are all the hanging weights. Now, right before I plug in the speeds, and I got a calculator, but I will do that real fast. 2 pi times radius of 0.4 meters divided by, whatever time I plug in. Okay. All right, now, right before I plug in these values, let's do a quick hypothesis. As you make that hanging weight heavier and heavier, do you think you'd have to spin it faster or slower? What do you guys think? Probably faster, right? By the way, the commonality among all of these graphs is going to be relating everything to speed. Remember, think about speed kind of like a dependent variable. It's just the easiest way to do this. Should be faster. Let's see. So the first one went 4.57 meters per second. That looks about right. Meters per second. Let's see, what's the next one? Goes for one. 6.13. 6.13. All right, next one is, also 6.13. It's at the same time. Then, all these times are pretty close to each other. I've got 6.28. 6.3 again. And 44. Looks like 5.71. And the last one is 7.18. All right. Actually, that's about what that should look like. All right. So the very first graph, you guys see the one on the top left that says V versus weight hanging? The top left graph says V versus weight hanging. That is that graph right there. You guys are looking at it. So go ahead and take that graph. The vertical axis is speed in meters per second. Thank you. The horizontal axis is force, which of course is the same thing as weight hanging, since that was supplying the force, and that would be in millinewtons. So draw and label those axes, scale them about like they are, put those points about where they go. And as you guys are plotting that, let's think about what that graph says, what the relationship is. So back at the very beginning of class, I'm talking about a few weeks back, I sketched out a handful of common graph shapes that you see over and over in this class. So there's like no relationship, either a horizontal or vertical line. That's definitely not that. There's direct relationships, right? So if you triple one variable, the other variable also triples. Do you think that's a direct relationship? Probably not. Like it looks like maybe linear, maybe, but if it was linear, do you guys see how there would be a huge y-intercept? And think about what that would mean physically. That would mean that for zero force, like for zero weight, there would be some discernible speed that it'd have to go at. That doesn't really make a whole lot of sense, does it? Right? There could be here's one of the other graph options, like inverse relationship. As one variable gets bigger, the other gets smaller. And it's definitely not that, which is good. And then the last couple were that you commonly see in this class could be like either a power relationship or a root relationship. Hey, is that a good candidate for what's going on right here? Could this be maybe a square root relationship? You guys know what square root looks like, right? Isn't it like a curve that kind of hooks down? That's probably what that is, isn't it? It's probably a square root relationship, right? Let's suppose that we suspect that. Maybe it's some kind of root, which could also be a fraction power, like x to the 1/2 kind of deal. Now, if you suspect that that might be the case, then we're about to do some axis manipulation. Now, this is something that we've done before. So watch this up here. I'm going back to just math basics, just y versus x, right? But you guys, of course, have like v versus f, but same idea, it's just variables, right? So very generic, y versus x, y equals the square root of x, just keep it very fundamental, might be doing something like that. So if x is 4, y is 2. If x is 9, y is 3. Okay, and then you plot all those points. There you go. Right. That's the same thing as a fraction power, like y equals x to 1/2. Right. But what if you didn't know? Is that a cube root? Is that a fourth root? Is that x to the 0.6? Or I don't know. If you suspect it's specifically a square root, what you can do is you can square both sides of this equation. Because if you square both sides of this equation, would you get something that looks like y squared is equal to x? Is that what that would look like? Y squared is equal to x? Right. That's this line right here. I'm just reminding you guys something that you've seen before in this class. We've done this before. Right? And then, so this says the same thing as this says, just from a different point of view. Square both sides is still consistent internally. You can actually manipulate the axes and have not y versus x. The original one was y versus x. You've seen that a million times. Y squared versus x. Right? And if you got that relationship right, if it was indeed a square root relationship to start with between y and x, then this should actually line up in a straight line, right? So y squared is proportional or equal to x in that case. Right? It says the same thing, right? So you've seen this before. Right? That's what we're about to apply to v versus f. So I wonder what v squared versus f looks like. Now, on your guys' lab page, on the back at the very top, you guys see on the back at the very top, see where it says v squared versus weight gain? Right? You guys see that one? Back to the top. Right. I'm about to scroll over, and we're going to take a look at what that graph looks like. Right. So same data. I set up Excel ahead of time to graph it for us, and oh, look at that. Right. So that is closer to a direct relationship, isn't it? And if I add trend line, yeah, ideally, the textbook answer, that would have been a direct relationship that goes through the origin, but that right there is not too far off. That's pretty much what we're looking for. Right. So go ahead and graph that. The vertical axis is v squared. The horizontal axis is force by weight. In millinewtons, of course, because doing millinewtons yesterday. V squared. What units does v squared have? That'd be meters squared per second squared? Sure would be, wouldn't it? What does that physically mean? Nothing that I know of. It's kind of an abstract idea. But mathematically, it reveals the relationship between v and f. So see, oh yeah, it verifies that this is between v and f was a square root relationship. All right, you guys got that graph? All right, so move on to the next variable. All right, so the one we're about to do, while you guys wrapping this one up, is what if instead of changing out the bottom Play-Doh canister, what if you left that one alone, and you left the radial size alone, but you changed out the mass of that top canister that was actually swinging in a circle? That's one we're about to do. So who wants to share their data who was doing that, who was changing out the mass of the swinging canister? Who wants to share their data? Yeah, do the same thing. I'm gonna take a trip around the room and see who has data that would be consistent with that. Changing out the masses. Oh, I think this one. Yeah, I'm gonna borrow this right here. Yeah, so, thank you. So, got another anonymous volunteer. And the masses go see, 106 grams, 205, 246, 36, 226, 20. Okay, so those are the masses. Oh, well, hold on, did I miss one? 106, 205, 46, 136. Oh, here we go. 146, 226. 20. So same thing, right before I plug these in, let's do a quick hypothesizing. As you make that top canister more and more massive, how do you think you'd have to spin it in response, faster or slower, as it gets more massive? Probably a little slower, right? You guys think that the graph that you're about to see is probably going to be an inverse relationship? Probably? I hope so. Let's see if it is. So. Yeah, look at that. Inverse relationship. Thank you. Inverse relationship. Exactly like you guys just hypothesized. Yeah, as the swinging mass gets more massive, you actually have to swing it a bit slower to maintain a horizontal circle of constant radius. Yeah. Right. Forgot. You guys do know that's the bottom left graph on the front, right? So the one, I'm sure you guys are already making that, but on the front of your lab, there's the bottom left graph says V versus mass swinging at, of course, constant weight and radius. So that's one you guys are making right now. So the vertical axis is speed in meters per second. The horizontal axis is mass in grams. Scale those axes about what you see on that Excel page. Put those dots about where they go. And yeah, there's definitely an inverse relationship. All right, so where are we going with this? Well, I want to know exactly what is the inverse relationship. We're going to do another axis manipulation just like we did for last graph and that we have in the past. And the manipulation is going to be, we're going to take the reciprocal of one of those. Let's take the reciprocal of the mass and then replot it and see if that produces a direct relationship or not. It might be a direct relationship once we do the reciprocal, or maybe not. Maybe there's going to be a step after that. We're going to find out. All right, so since you guys are finishing up the bottom left graph, look to the graph right to the right that says V versus 1 over M. You guys see V versus 1 over M? It's the bottom right graph on the front. V versus 1 over M. You guys see that? That's what you're about to see right here. So Excel is pre-programmed to just take the masses, take reciprocal, plot it. Okay. Oh, that is exactly what that should look like. Yeah, V versus 1 over M. There you go. So speed in meters per second is the vertical axis. The reciprocal of the mass in 1 over grams is the horizontal axis. So label those axes, scale them like you can see, put those points about where they go. I forget if I mentioned this yesterday, but this is definitely one of those labs that if you were really meticulous in your measurements, like keeping the radial size constant per trial, and you were really good with the stopwatch, if you took really good measurements, then that would definitely be reflected in the graphs. Like the graphs definitely reveal how good a job you did with your data collection. And that is pretty much exactly what that graph should look like. So definitely good job for you and your team there. Yeah. So V versus 1 over M. Now that's a step closer to that direct relationship, which would tell us exactly what relationship is. But that's not exactly a direct relationship, is it? It has a kind of a curve to it, doesn't it? What kind of relationship do you think that is? It's another root, isn't it? Another root relationship. That looks like square root of x, doesn't it? Y equals square root of x. Okay. Which means we're just going to do the same thing with this one that we did with the very first experiment. Okay. So that's to say we're going to square the v. So we'll have v squared versus 1 over m, and then replot that data. Right? Make sense? This is the second graph on the back. You guys ready to flip over to the back of this page? You guys see the middle graph says v squared versus 1 over mass at constant hanging wave and constant radius. Okay. So let's see what that looks like. Oh, look at that. It's a direct relationship. This is the middle graph on the back, the v squared versus 1 over m. So this is started with v versus m and then has gone through 2 manipulations to get to v squared versus 1 over m. And that happens to line up in a direct relationship. Woo! Now we have another relationship pinned down. Okay. Now, while you guys are drawing that one, what I want you guys to notice too, and some of you guys may notice this, those three graphs on the back, you guys see the three graphs on the back are like leading straight into the answer. Okay. Notice they're all v squared versus something. The one you did a few minutes ago, the top graph, says v squared versus weight gain. The one you're doing right now, the middle graph, says v squared versus whatever mass. And the one we're about to do in a few minutes says v squared versus radius. It's always v squared versus something. Now, why is that? In general, because all these variables we have to link together, so they have to all be related to something. And it just happens to be, there's many different ways to do this lab, but the easiest way to do it is the way that we're doing it. It just happens to be that the easiest variable to link them all to is the square of the speed. Thinking ahead a few steps, but some of you guys may have noticed the titles and kind of see the pattern and see kind of how this is going. Okay. So the square of the speed versus the reciprocal of the mass is a direct relationship. Ooh, that's a funny one there. All right, well, we've got one more relationship to nail down. We've got one more variable to incorporate, and that's the radial size. So who wants to share their data who was in a group that did not touch the Play-Doh canisters the entire experiment, just left those sealed, but was changing out the radial size? Eddie, you gotta, let me see. So scroll over, scroll down. Okay. So Eddie, what were your radial values? Yes.
0.24.
0.24?
0.34. 0.47. 0.67. 0.2. 0.14. That's all we got.
All right, that will work. And let's right before you tell me the speeds, let's do some hypothesizing. Now this is maybe the toughest one to figure out, maybe. Right. So what do you guys think is you're about to say? Say if you increase the radial size, you make circles that are bigger, bigger, bigger. Do you think you'd have to swing a little bit faster or a little bit slower as the circles are getting bigger? Well, let's find out. So Eddie, what were your speeds?
First one is 3.31. Next one is 4.05. This one is 4.82.
You say 4.82?
Yeah, 4.82. Yeah. And then 6.2, 2.86, 2.44.
Oh man, this class did such a good job with these. Yeah, that's exactly what that graph should look like to you. Yeah, so thanks for sharing that data. Oh man, the class is 3 for 3. Yeah. So speed versus radial size. Right. So the way I phrased that question for hypothesizing was, if you increase the radial size, what do you have to do to the speed? Okay. Well, according to that data, you'd have to actually spin it a little bit faster, wouldn't you? Okay. But it's not exactly a direct relationship. Like if you double the radial size, you don't have to double the speed. It would be less than double the speed. In fact, you know what that looks like? Doesn't that look like possibly another square root relationship? Yeah. Sure does, doesn't it? It's some kind of root going on. Now, while you guys are copying this down too, I want to add a little bit of commentary to this. So I normally teach this class in a different order, except that AP goes with a certain way, and the honors textbook also goes the same way AP does. So anyway, what I'm trying to say is that usually when I do this lab, I've already given you additional information, which is that there's actually a different kind of speed. There's a different kind of speed that we haven't talked about yet in this class called angular speed or angular velocity, which is not how fast is something going like meters per second, but it's how fast something's spinning. So classic example could be like the spin of the Earth. Right? No matter where you're standing on the Earth, isn't there one revolution every 24 hours? Right? Sometimes I say the Earth is spinning 1,000 miles an hour, but that's really only true if you're kind of near the equator. If you're up near the pole, that linear speed gets close to zero, doesn't it? So like the linear speed depends on your latitude, but no matter where you're standing on the Earth, you get the same angular speed, which is one revolution every 24 hours, right? You guys ever heard of like RPM, revolutions per minute? Okay. That's a way to measure this other kind of speed we haven't got to yet in this class, which is angular velocity, angular speed. But we usually quantify it in radians per second. Now, why am I bringing up all this? The reason I'm bringing this up is because if you had hypothesized the other way, you said, well, as you increase the radial size, maybe you should swing slower, if that's what you were thinking, you would actually be right for that other kind of velocity, for angular velocity. There's actually a slower angular velocity, even though there's a faster linear velocity, like radar gun speed. So, and that's really all we've done so far in this class, just linear speed. Okay. All right, you guys got this? Well, you guys know what the last axis manipulation is going to be, because we've already done 2 of them, and the last set of axes is set up for this. Okay, so flip over to the back, and remember, you guys just did the top right graph on the front. So on the back, the very bottom one says v squared versus radius. Right? So, yep, v squared versus radius. Moment of truth, last one. We're going to see what this looks like. It should be a direct relationship. And drum roll. Oh, look at that. All those points line up in a straight line. Oh, yeah. What a good Friday. That trend line. Look at that. Straight as an arrow. V squared versus r. Yeah, so now you guys know that, for example, if you were to like quadruple the radial size, you would have to double the linear speed to maintain dynamic equilibrium for the top one. Right? Remember, it's not true static equilibrium for the swing one because there's a net force, but here, called centripetal force. So to maintain the size of that circle, if you have 9 times the radius of the circle, you'd have to triple the linear speed. So, tough relationship. Yeah,
On the way you're done, could you go back to the second graph for a second?
Yeah. Oh, you mean the second graph on the back?
No, on the front.
The one we just did?
V versus radius.
V versus, maybe I can get these side by side. Try that. There you go. Right, so, well, there's V graphs. So, V versus R on the front, V squared versus R on the back. Yeah, all right. You guys got all the graphs? All the graphs?
Maybe the first one on the back.
Oh, the first one on the back. Looks like this up here. All right. Here you go. All right, so, well, I guess it's panning out here. We're gonna get a big picture view. So V versus F was some kind of square root. Start with the 4 on front. So V versus F square root. V versus M is a reciprocal. V versus 1 over M is a square root. And V versus R is a square root. The 3 on the back are all linear relationships, but they all involve axis manipulations. So V squared versus F, linear. V squared versus reciprocal of the mass, linear. And finally, V squared versus R, linear. Okay. That's good. Okay. You guys ready for equations? Good. All right, so flip over to, let's see, stop sharing my screen. Projection. All right, so now we got to put this all together. Now, there are a couple boxes at the bottom that are the same idea, but just from 2 different points of view. Okay. So basically, how are these 4 variables related? Remember the hanging weight, the swinging mass, the radius of curvature, and the instantaneous speed? Okay. How are these related? Well, the 3 graphs that you guys are looking at right now lead straight to the answer because v squared is directly proportional to, well, some version of each one of those other variables. It goes like this. The top graph says that v squared is proportional to the weight hanging. Now the weight hanging, instead of weight, I'm going to say F sub C, because remember that hanging weight provides the tension, which provides the centripetal force. So I'm going to call this centripetal force. And the whole point of this lab is to figure out what is an equation for the force of moving in a curve. That's to say, we're trying to figure out what is that? What is centripetal force? Is a function of everything else. The second graph told you that v squared was proportional to the reciprocal of the mass. So I can turn this into a fraction and put mass down in the denominator. And the very last graph that you guys made said v squared is proportional to the radius of curvature. So I can put that in the numerator right there. Okay. That is what goes in the bottom left box. Say v squared is proportional to, it's that right there. Okay, so the bottom right box says, therefore solve for force, like that's to say centripetal force. All you have to do is algebraically rearrange this. Okay, cross multiply up this mass, divide down the r, and centripetal force, like a center-seeking force, F sub c, centripetal force, is equal to, sorry, not equal to yet. Let's say proportional to. That's all we really proved so far. Proportional to mv squared over r. Okay. Now, this proportional to means that there's possibly some of the equation that we're leaving off, maybe a 1/2 factor, maybe other variables that we didn't account for. Maybe it was like if you double the temperature, it throws, I don't know. Right? So proportional to means that there's possibly more to the equation. But you know what? It turns out that if you multiply the three slopes together, the slope times this slope times this slope, it exactly equals 1. All the units cancel. So you can actually go one more step, and here's the textbook answer. Centripetal force turns out to be exactly equal to mv squared over r. Okay. So we proved proportional in class, but I guess if you got really precise measurements, you want to go dig around and prove those too, you could actually say equal, and that is true. Okay. You know where else that shows up is here it is. On AP equation bank, let's look at this one right here. Let me show for the camera. Go zoom in here. It said there's an equation that says centripetal acceleration is equal to v squared over r. Ooh, that is actually what this is, because to go from force to acceleration, don't you just divide by mass? Okay. So the one printed on the AP page that you're allowed to use in May almost says this, except it says centripetal acceleration is equal to just v squared over r. Okay, I say that? Right. A few other things I want to say about this. One is that centripetal force is never a force unto itself. It's always provided by one of the classic forces that you're already familiar with. So it could be tension in a string. It could be some weight. Could provide centripetal force, like if something is in orbit around a planet, like a gravitational force. It could be a component of a normal force, say like from a banked wall, if a car say going around a curve on a banked wall. But there's always some force that's acting as the centripetal force. Right. The other thing I want to do is give you guys another example, because one example you have is just the entire lab that you did yesterday that involves like all this stuff going on. But how about this? Let's say you're in a car. Let's go back to the car that I keep bringing up since the beginning of this class a few weeks back. And you turn the steering wheel and you start going around a curve. Well, what would actually even allow you to go around a curve in the first place? Well, it's going to be probably one of two things. Either friction between the tires and the road, if it's a flat road, right, that could provide centripetal force, but that would be a friction force, wouldn't it? Right? Or if it's a banked road, it might be that you don't even need any friction. It could be like an icy road that's just banked. You could still go around a curve, and that would be the horizontal component of the normal force. That could be an AP question, because I've seen AP ask exactly that question in the past. If the road is banked and the car's going around a banked road, it would be the horizontal component of the normal force that would be acting as this force. And then what would that force be equal to? It would be equal to the mass of your car multiplied by the square of the speed of your car. So you look at the speedometer, it says like 30 miles an hour. You could, right? So that's the speed of your car, all divided by the radius of curvature of that curve. Right, there you go. Any questions about that, lab? Right. There is another thing that I had you guys do, though. I had you guys do this 5-question write-up, but we are out of time for that today, since today's a short day. So we're going to have to go over the 5-part write-up on Monday, but I do have 3 separate ones ready, depending on which experiment that you did. So I'll get you guys that on Monday, so you can grade yourself according to an AP style rubric. Right? And that is a wrap on Friday.